Good morning, good afternoon, good evening, depending on where you're viewing from or possibly later on. Just to reiterate, my name is Dave Eckroat. I am the director for IDEA StatiCa here in the US. I have with me, as usual, Andrea and Jan as our team. So we're just going to give it a second here to let people log in, and then we will get started with the presentation. All right, why don't we go ahead and get started? I know we have a lot of information to cover today. Thank you again for joining the latest webinar from IDEA. Andrea, if you can move to the next slide. So just to kind of, I know probably everyone's used to using GoToWebinar over the last couple of years, but just a quick screen to show you the control panel, kind of where you can switch between audios, send any questions in for us during the webinar, and hopefully, you'll find it very informative. So just to go over what our agenda is, we're going to do a very brief introduction of CBFEM. Then we're going to move into how welds and bolts are modeled using CBFEM. We'll go into some options for modeling with welds and bolts, talk about some design results, and finally look at some of the detailing checks that IDEA StatiCa can run on your connections. So CBFEM, you may or may not kind of know the term. It's component-based finite element method. This is the method that IDEA StatiCa uses to analyze joints and its components. And really, it's kind of a hybrid of component method and finite element. Obviously, the component method is separating out all the different components of the joint and looking at them individually. The problem with that is that you are just kind of you're not looking at the combined joint or the combined effect of loading on a joint itself. So by adding in the finite element method or part of it, we're able to take advantage of kind of both methods as far as finite element analysis to be able to get your stresses and strains based on the material properties, as well as component-based method to do some specific checks of particularly welds and bolts per the AISC code equations. So now if we look at how IDEA in particular breaks up different components of a joint. So if we look at beams, plates, angles, any of kind of the main member type components of a connection, we're using shell elements. So you have 6 degrees of freedom in each node. The software is auto meshing each of these components, and that mesh is based upon severe testing we've done to kind of figure out what the best solution may be for the mesh size to optimize both analysis results as well as time of analysis, basically speed of the program. If we start to look at bolts and welds, the welds are really a shell element, but it's an elastoplastic element that Andrea will get into a little bit further. As far as the bolts and welds, they're being modeled as nonlinear springs. And then once we get the loading on those elements, then we're comparing them to the AISC equations, as I mentioned. As far as the node, that's kind of the central point. That's where all the members are intersecting. And that's kind of where all the loading is going to be based off of. And then finally, we can look at some contacts. So surface to surface contacts, edge to edge, edge to surface. We do have some contact within the software. So with that, I am going to hand off to Andrea so she can discuss a little bit further.
All right, so my audio, it's okay, right, David?
Yes, can hear you just fine.
Perfect. All right, so yeah, thank you for that introduction, and this is obviously a summary. I will go more in a further explanation of welds and bolts and how we model it in IDEA. Okay, so you can understand from where we are getting those results. Okay, so the first topic that I am going to talk about is how we transfer loads from one member to another. So when you are reviewing results and activate the mesh view, sometimes you will see different mesh densities between members. You may wonder how that is possible, or why we have different mesh densities between some plates of the element to another. Well, here is the explanation. The load is transmitted through force deformation constraints, call it multi-point constraint, and that relates the finite element nodes of one plate H to another. The advantage of this approach is the ability to connect meshes with different densities, and the load distribution in the wall is derived from this MPC. So the stresses are calculated in the wall section. This well simulation approach is used for full penetration welds. Okay. However, this model doesn't consider the weld stiffness, and the stress distribution is conservative. So stress peaks, which appear at the ends of the plate edges or corners, controls the resistance along the whole length of the weld. So to remove that effect, a special elastoplastic element was added between the plates and the MPC. So here you can see in this diagram the plate, let's say the 3D plate, and how we do that mesh for the vertical and the horizontal plate, and then how we connect, or how we use the multi-point constraint to connect one node to another node, and between that joint, let's say, we have that equivalent wall shell element. So that is the shell elements that are in purple here in this diagram, right? So let me just use this laser point. So you here can see this small rectangles that are representing the equivalent wall shell element. Okay, so let me go to. So that element considers the weld throat thickness, position, and orientation. And the elastoplastic behavior is considered in the material nonlinear analysis that the software does with this model. So the stress peaks are redistributed along the weld length. This is an effect of using elastoplastic material. The elastoplastic model of welds gives real values of stresses, and there is no need to average or interpolate the stress. Okay, so also you can see that let's say mesh of that weld in when you activate the mesh view, and the equivalent stresses in the main model. So let's go to that part of the software. When you are here in the check tab and you have already results, you can activate those here in equivalent stresses, and you can activate the mesh view over here. Okay, so I was pointing here, this one. Okay, this mesh view. So here you can see the mesh that was used for the weld. For instance, here you can see 7 elements. If you count down this, 7 elements in that mesh. But also you can see those 7 elements represented in this part of the screen. And those 7 elements are represented as a bar graph with the maximum and minimum equivalent stresses in the mesh elements. So you also will see the same amount of elements here in this graph as in the graphical view of the mesh. All right. So IDEA StatiCa calculates stresses on those shell elements of the weld, and a critical element from the whole length of the weld is selected. And then the force and theta angle is calculated from it. These are simple geometrical calculations, so we get the Fn that you can see here, and from there we calculate also the angle between the Fn and the longitudinal axis of the weld, so we can use that information into the AISC checks as well. Also, later you will see this LC, that is the size of this element of the mesh of this full weld. Okay. All right. So when modeling weld operations in IDEA StatiCa, we have the next options here. You'll see when you have welds in any operation that have welds, you need to input the leg size. Okay. So what is the leg size? Here you can see a section of, let's say, a weld, and this is what you're inputting, the leg size over here. Okay. Then you can select between fillet welds or CGP welds, one side or double side fillet welds. Okay, here you see, and it is useful when you activate the 3D solid view, so you can see where that weld is being located. Also, there is the option of no weld. Maybe you don't need that weld in that operation, so you can just turn it off, right? Then we have the option that the user can input 0 in this value of leg size, and when you input that 0 there, for single-sided fillet weld, the weld throw thickness is going to be equal to the thinner connected plate. Okay, and then for double-side fillet weld, the throw thickness is going to be equal to half of the thinner connected plate. So that just gives you the minimum requirement for that connection, right? Okay, so why I was explaining this? Well, this is to understand results here, where when you're again in results and you select the welds tab in results. Okay, so here you will see all the welds items like in a list. But if you click on, let's say, this plus icon, you will get this calculations, AISC calculations, right? So let's understand what we have in this table. So you will see where is that weld located. I mean, that line of weld when you select here in the table. So that is on the C top flange. So C member, in this case, is the column. And here you will see highlighted that weld that you're, reviewing results in orange over here. Okay, so then in which edge you have that, so that's in the fin plate, so that's this fin plate. Okay, and then you have this TH value, so that TH value is the throw thickness. So how we calculate that, we use the leg size that you input here, we multiply that by Casino 45, so that was the previous calculation that I had here, so that's how we calculate that throw thickness. Okay, and you will see the leg size that the user input here over here. Then you have L, so that is the length of the full weld, so that is the length here, in this case 8.83 inches of this weld. Okay, then we have LC, that is the length of the critical element, so that is the length of one element of the mesh, okay, of that weld. Low LE1, that's the critical value. Okay, and then finally we have the Fn, so that's the resultant force from the most stressed element in the weld. Okay, then we have the Rn, that is the weld resistance check. So you can see that calculation clicking again in that plus icon, and here you will see the angle of loading that was also calculated from the finite element analysis. Finally, we have this effective area of weld critical element, so that will be LC multiplied by the throw thickness. Okay, so we are just getting the area of that the most stressed element in the weld, right? So this is how we calculate that area. And of course, the utilization percentage, you will see it over here, right? So that's how we, well, how we present results. In case you want to do some hand calculations or review what we are giving to you, I always recommend to change this to decimals. Sometimes if you have imperial, you will not get the exact dimensions. So I recommend to change it so you can test that those values. All right. Okay, so the next thing is that I have here in these slides. When you add a weld operation, we have the option to add continuous, partial, or intermittent weld. So that's when you select weld operation. Okay. Also in that weld operation, we have I have this like trick to show you. You need to select, this is the placement or the type of weld that it's edge to surface. So the first plate is you need to select an edge to connect to the second plate, right? So here you select the plate that you're going to connect to, and you select edges. So when let me go here. When you're selecting edges, sometimes you add 3 different weld operations. So instead of adding 3 weld operations, you can just put the edges that are in the same plate. So here you can see SP2, and we are connecting edge number 1, 4, and 3 to this plate of the column, right? So you just place those, put the number, space, the next edge, and the next edge. So you can save some operations over there. So that's kind of a trick. Okay. All right. So one thing that you can modify from code setup, for welds, is to check the base metal capacity versus the weld metal. And from that idea, we'll select the lower value and compare versus Fn, that it's the force calculated from the analysis. Okay. That option is not used as default. So if you want to use it, you have to open code setup and activate it. So every time in this presentation, I am putting the icon where you can find this code setup. And here is the option that you can toggle on or off. Okay. And here I am showing the part of AISC where that is mentioned. All right. Okay, so let's talk now about bolts. I won't go through too much detail on this, but if you need more information about the formulas we use to calculate the stiffness here, you can go to our support center and look for a theoretical background. You will find a lot of information over there. Okay. Anyway, so in the CBFEM method, the bolts are described as nonlinear springs. Okay, so a bolt in tension is described by spring with its axial initial stiffness, design resistance, and initialization of yielding and deformation capacity. Okay. When the yielding starts and deformation capacity, it is assumed that plastic deformation occurs in the threaded part of the bolt shank only. Okay. And then, here you will see also the load deformation diagram of a bolt in tension, in shear, and how that bolt tension force as function of deformation in shear and tension. So again, if you want more information about the formulas that we are using to calculate these values, those are in our support center in the theoretical background. But the main objective of this slide is to show you that we use nonlinear springs. All right. Okay, so now when you're modeling bolts in, let's say, in our operation, you have the option where it says shear force transfer, and if you click in that drop-down menu, you can select the friction option. So that will create a slip critical connection. Okay, so when you change it to to friction, then the formula J4 from AISC will be used for calculating the single bolt available slip resistance, as you can see here, okay? And from here, you will see some different, calculations, right? So also factors. So I'll show you how we can modify that. But yeah, so you can modify this when you have bolts in one operation and click on shear force transfer and select from bearing or friction option. Okay. The first factor that you can modify is, well, either if you are using LRFD or AISC, okay? So you can change the slip resistant factor, and here you have the option where it says slip resistant joint for LRFD, and the foul value is 1. So that means you're using standard size and short slotted holes perpendicular to the direction of the load. And if you want to use oversized or long slotted holes, you may change this factor, okay? And you can do that clicking on code setup and changing that factor over here. Then, in that formula, in that J4 formula, we also have the factor for fillers. For one filler between connected parts, we use HF as 1.0, and for 2 or more fillers, we use 0.85. So fillers are detected automatically, and the factor is changed in IDEA StatiCa. So there is nothing that you can do there. So a filler is recognized by IDEA StatiCa as an inserted plate that it's not connected to any other weld or bolt grid. Okay. So you will see that when you're seeing results in the bolts, you will see that HF factor. So you will see if that was changed or not. Okay. Okay, also you can, from that formula that I show you for slip critical connections, you can modify the friction coefficient in a slip resistance. So that's also in COD setup, and you can modify from 0.30 to 0.5 as it is stated in AISC. Okay, here I have the formulas. I will share this with you while in the site where you register to this webinar, you will see this presentation available to download. Okay. Now, talking about bolts in bearing, there is an option in AISC to change, let's say, the factors when the formation at the bolt hole at service load is a design consideration or not. So you can activate that option as well in code setup. Okay, so I am giving you all the options that we can modify from code setup for, well, to model correctly the bolts in IDEA StatiCa. Also, well, it's known that we can use fillers in bolted bearing type connections. Okay, so if you also have a filler over there, the filler is detected and the reduction is applied. So here I am showing a part of the results in IDEA StatiCa. Okay, this is a formula that was used in one calculation, and this was used with bearing bolt, and I had a filler, so that factor was detected, and then that is also changed. So you can see here the R factor, so that's reduction factor for fillers, and here we have the reference. So that will be detected automatically. All right. Also, we have the option to add standard or slotted holes. That can be done in the editor of plates when you are locating an operation and it has bolts. So you click on editor, and then you can come here to editor and change the slotted, well, to vertical or horizontal slotted holes. So when you change that, well, you can see here, bolts in standard holes can transfer shear force in all directions. If you change it to slotted holes, one direction is excluded, and there the model can move in the selected direction freely. All right, so that will move freely in this direction, for example, in this screenshot that I have. Okay, so maybe you can have some errors, or the analysis won't finish because you have to take into account that in one side, well, in one direction, that's freely moving all the model. All right, so that's something to take into account. Also, when you're adding bolts in your model, you have the option to activate share planing thread. So if you activate that, we are going to use these values that, for example, it says bolts when threads are excluded from shear planes or when are not excluded. So that nominal shear strength change. So I think it's for this ones that changes. So if you activate that, you know that we're going to change this nominal shear strength. Okay. So that's something to note. Then another tip to consider when you're modeling is that the maximum distance allowed between two connected plates is 0.08 inches. Okay, so that won't tell you an error in the when you're running the analysis, but if you don't find where you're having that let's say error in the analysis, or it doesn't run, you may check those gaps. Okay, because the maximum distance allowed between those plates is this value 0.08 inches. So be careful with this, right, when you're locating plates or whatever. That's why I like to use when you're modeling a plate, to use the origin from one face of the member or a plate. Okay. All right, so now let's talk about detailing checks. We have detailing checks in IDEA StatiCa, okay, based on AISC. So you can activate those for, let's say, bolts and welds, clicking on the code setup, and you have this line that says detailing. You can activate that. That is not activated by default. You need to modify that, so you can activate that. And then you run the analysis, and if you have a detailing checked failure, let's say, you will see that on the summary of analysis when the analysis is done. Let's say you have a failure in the detailing check. How you can review that? So you go, for instance, to the bolts tab, and you have to click here on the plus icon. There you will see all the checks for bolts. Okay. And you have to scroll down to the last part of that report, and there you will see where is that detailing check, or where is that failure. For example, in this case, this bolt, the B1, because we are seeing the B1 results, is too close to bolt B2. So this will tell you what spacing is needed for that type of bolt or for that diameter. Okay. So for bolts, we have this, we use the minimum spacing from AISC, and also we are reviewing the minimum H distance. Okay, so we are using these two sections of AISC. The minimum spacing between bolts is 2 inches 2/3 times the nominal diameter. Okay, and here we have the minimum H distance for the different bolt diameters as well. So we are following this for those detailing checks. When you have, or when you activate detailing checks for welds, that it's the same checkbox. Okay, We are going to review the minimum size of fillet welds depending on the thickness of the plates that you're connecting. Okay, so we use this table to review that check, and it is the same. You will see a new column when you're reviewing Welds results that will say detailing. So if you see a red cross there, you have to open that report and scroll down to the results and see the detailing checks over there, and that will tell you what is needed over there. Okay, so okay, let's review this summary. Okay, I know that it's a lot of information. We have this information also in our support center, and I will share this presentation. And but this is like the main summary. For welds, we use elastoplastic shell element. So that allows plastic redistribution of the stresses in that weld. We can use fillet, CGP weld. We checked minimum weld thickness required by AISC. And then for bolts, we use nonlinear springs to model it in IDEA StatiCa. We can select slip critical connection. Fillers are auto-detected, so you don't have to do nothing about that. We can select slotted holes, and we have detailing checks also for bolts based on AISC. All right. All right. So I'll go through some questions that maybe we have, and maybe I can show you the answers there in the software, directly in the software, so you can see what we are doing over here. Do we have some questions, John? Or
yes, awesome. Thanks, Andrea. Yes, we do have some questions, but feel free to keep adding questions to the chat if needed. Let's just take it in order. So there was a question about last webinar, actually, asking about how to place members compared to each other, how to align different beams, for example. And we do have the option. There's a drop-down menu when you're looking at a member. Andrea is showing it now, where you can align a member to another member plate, meaning align for example, a beam flange compared to another beam flange that has already been defined. There was a question about screenshots. So of course, this webinar will be posted online, so everything will be available to everyone soon. And then several questions regarding PJP welds, which are not yet implemented in the software. This is one of our priorities that will be coming soon. It's in development, but we don't have a date at the moment. There was a question about the K factor, so the directional loads factor for fillet welds, which should not be included for HSS connections. Currently they are, but we're working on removing them per the latest AAC codes, 15th edition. We're working on removing them from our calculations. I mean, removing the loads, the directional load factor.
The angle, right?
Yes, correct. And for the oversized holes, so currently we don't have or we have workarounds only to be able to create oversized holes. This is by going to the materials tab and copying a bolt assembly and changing in there the size of the holes that you would like to see. So, for example, what Andrea is showing there, we can copy and then manually change a bolt hole or hole diameter. I mean, hole diameter.
Yeah, just important information there. I mean, you can do that, but that won't change the analysis. I mean, that won't change nothing in the analysis.
Yeah, the analysis behind it is going to be the same. Yep, correct. Then a question regarding the threads being included in the shear plane. Or so yes, by default in any bolt operation, the threads are going to be included. So those would be end bolts. But when we're looking at any bolt operation, you have the option of untangling the shear plane in the thread, making those X bolts. And then other questions regarding Canadian codes. Yes, we do have the option of creating connections following Canadian codes, not just AISC. We have, I believe, 7 or 8 different codes, including Canadian on top of American, the European codes, and some other codes around the world. Is it possible to save our code setups settings for further calculations? I do not believe so. I think you may have to check it every time you will create a new connection and copy your parameters every time, I believe. I'm not aware of an easier way, at least. And David, if you want to jump in as well, the questions are coming right now, so I'm reading them at the same time. Is the minimum size weld check based on the thickness applicable to only AISC, or does it check this based on other codes, for example, Canadian? That's a good question. I know it does it for the AISC. I believe it would be similar for the Canadian and just follows the Canadian requirements, but I'm not 100% sure on this one.
I'm just checking, but I think we have a site. If you review this, there is a theoretical background article that it's check of steel connections components for the Canadian code. So maybe that will be there. I'm not 100% sure. Just check this. Detailing for bolts, and let me just go here. Sorry, I'll need to double check for welds, but yeah, we can follow up on that question.
Okay. For situations in which a member has to be offset manually with a set distance and not a cut, does the force and position measure from the new offset point or the original work point? I believe it will always be according to the node, and you can view that node by going to the wireframe view. So if you were to play and then say forces are not in the bolts or in the nodes, but in position, and manually change this, you will be able to easily see where your point of zero moment is.
No, but just to clarify that, I think he's right. If you see this part of the screen where I am changing to forces in position, the position of forces in the member, the position includes the eccentricities used for the member. So that includes, so it is adding that eccentricity of the member that you did. All right.
Awesome. Can we model shear studs on beam top flange? I don't know if you can model it, but you can. You have a new operation for lateral torsion restraint that allows you to add that. Yes, Andrea is showing it there. That this is something that has been added in the latest version in April that will allow you to include that torsional restraints in your elements. If I model an end plate which is flush with the top of the beam flange, and I add a double-sided filled weld, what does the software do? Can I manually use a PJP in my connection, or is this invalid? For this, I would recommend using a CJP, and if in reality you have a PJP weld, check it on the side by hand until we actually have that operation in IDEA. This would be better to fake it with a CJP weld and manually check the CJP rather than providing double filled welds. will there be an option to ignore the load eccentricity of single angle member connected to a plate per AISC 360? This is something I would like to see being done. I am not aware of this being worked on at the moment, but I believe this is something we should focus on. So we'll pass that along to the developers and see if we can have this added to the software. What is the best way to create a PDF of the connection showing the welds and bolts? So Andrea, do you want to showcase that section?
Yeah. Yeah, so what you can do here is, let's say you want this drawing here. You right click and let me see. Do I have the correct maybe I don't have the correct license, right? That's why, because it's not showing me the section view. Sorry. Let me just...
So what Andrea is trying to showcase is basically when you are looking at, for example, that shear plate connection that she was looking at, you can click right and you will have a button there saying create section, if I'm not mistaken. And this would give you a 2D drawing of your welds and bolts that you could then use to print out, basically. So a small detail of your connection perpendicular to the element that you clicked on. Is there a way to download a complete detailed drawing of the connection? No, we really focus on the analysis side. We're not doing that much of the detailing. This is something that other software would be much better at doing. We can link to some software, and we're soon going to be able to send our information back to software like Tekla, for example, for you to be able to do that in other software. But at this time, we really focus on the analysis side, not so much on the detailing side. When I put a horizontal short slot, go for it.
Oh no, I was just going to say, I'd see there's a couple of more questions as far as the oversized holes. So yeah, I mean, we are working on adding the oversized holes and having the analysis portion of it. The challenge is that it's going to be similar. It would be similar to a slotted hole where you're basically going to have no contact. So you'd have to use slip critical bolts at this point to kind of take advantage of that and understand. As far as the analytical part, when you increase that hole size, it's going to show a larger hole for the bolt itself. What we meant by it's not doing the analysis or including the analysis is that it's not looking at, it'll look at that enlarged hole size, but it's not going to do any other checks for it. That is something we're working on. It's just a little bit of a complex situation when you're working with finite element analysis. And being able to get that to actually work in the method that we expect it to. So I just wanted to kind of, because there's a couple of questions about that, so I just wanted to answer those. Go ahead, Jan.
Yep. There was a question about horizontal short slots. So when we're using horizontal short slots in a standard shear tab, even with only 5 kip, I guess, of axial loads, why does it require slip critical bolts? Yes, the software is not going to like if there's no contact between the bolt and the edge of the hole, which would be the case for, and of course if the load is in the direction of the hole, which would be the case for such a connection with horizontal short slots with axial loads. So the connection will not run for that reason. There needs to be contact, and slip critical bolts are the only way around this.
And part of that, just to kind of add on, when you put regardless of how large the slot is, once you put the slot in, that bolt can basically move infinitely in that direction. So even though it's a short slot, and in reality, it would move and you would end up getting bearing. it's just difficult to be able to fully get the deformation of the member and kind of understand when that interaction, when that contact would occur. So that's where we're having, as far as the short slotted holes and or slotted holes in general, why it's such an issue, and kind of similar situation with the oversized holes. So I just wanted to kind of pass that information along too.
When I have a connection with both shear and moments, how do I stop the shear weld from adding to the moment of the connection? So I'm guessing the best way would be if you want to have the shear only going down, for example, in the shear plate without adding to the moment. That would be with playing with the point of zero moments and where you actually want to set the location, the application, or where the vertical shear load is applied. If there is an eccentricity in your shear, there will be a moment included, and the connection and IDEA StatiCa will take this into account in the weld and create an extra moment if there's eccentricity. And do you want to answer, David, or clarify the question about the oversized holes and the workaround in IDEA?
I think I already mentioned that.
Okay. And that was the last question so far. And of course, anyone can email any of us, David, Andrea, or myself, if you have any other question.
Yeah, we can give it another minute or so.
Just to show the section, I had let me just show you this. So to see the section view that I didn't have later, you can right click on the connection and you click here, create section. So you will have this view over here, and you can add that to your report. Okay.
And so there's a last question that came in. So if I move the point, so this is a follow-up of on the question regarding shear and moments working together. If I move the point of application to have zero eccentricity moment at my connection, and the member is falling away from the connection, is there a workaround for this? I'm not sure why that would fail, apart from if the member is overstressed.
It's actually so, yeah, I mean, just because of the way that applying that load at the node would basically kind of generate a moment, an additional moment in the member itself. So one option to potentially do that would be, it's a question of if those loads are actually being applied at the same time. The workaround may be, one option could be that you apply two separate load effects, one for the shear, one for the moment, and this way they'll kind of run individually. I just thought there was another kind of clarification for that. So that would be kind of one of the options to kind of as a workaround. Okay.
All right.
I'm not seeing any more questions coming in. Obviously, thank you for taking the time. Oh, here comes one. So yeah, we can, obviously appreciate everybody jumping in. We definitely left more time for questions. Since our last session, we were running over a little bit. I know there's a question, a different question came in about issuing continuing education units. We're not a certified provider of CEUs. That being said, so we're not necessarily issuing them. We're not certifying any of these sessions as far as with like NCSEA, Diamond, or anything like that. So typically each state has their own requirements as far as for continuing education. So if there was any further questions about that, feel free to reach out to me directly, and we can kind of discuss it.
I think the question is there, David.
Yeah, I'm seeing that. So did you want to answer that, Andrea?
Yeah, I think he's referring to this. Well, let me just read the question. There is a need to balance loads for a continuous bearing member. So I am not sure if you have seen this, but you can activate loads in equilibrium so that you can add loads to the bearing member. In this case, the bearing member is the C. And then when you go to load effects, you'll be able to add, let's say, the forces at the beginning of the member and at the end. So that's how you can input that information.
And I see there's another question. What does it mean, nonconformity, in the nonconformity column? And that's usually just some residual reactions from eccentricities and things. If it's just the when you run the check, yeah.
Yeah, and maybe because the load is not, I mean, the node is not in equilibrium, so that's why you have those extra moments that you're not taking in the model, or it is not balanced.
Right.
Right. Is still needed to balance these forces to the new versions.
It's the same question. So,
yeah,
but
it's
do
the
you
same.
want to
Yeah.
show the last one, how to export the connection to the XF?
Yeah. So we have an option to. This is the IDEA StatiCa viewer. Let me just open that really quick here. So that viewer is available. Well, it's like free to use. And if you have any project, you can just, let me just move one project that I have here. Okay, so if I send this here, you will see the connection, and then you can download this to 3D WG file, right? So that will export, and then you will have details of the blades and all the values. And then the other way to show details is you can create the section as I show it, and then if you go to any of the operations that has a plate, you can go to editor. This is where you can also change the slotted holes, and then you can click on drawing and you will get this drawing, and you can right click on this drawing and send that to the XF as well. Okay, so those are the ways to have information in a CAD software.
Right. And once you have that 3D DWG file, in your CAD program, then you can create your 2D views from that. And again, it's not going to be the perfect solution. We're not necessarily a drafting or detailing package, That's one of the things that, you know, we're definitely working on for version 23, is being able to export the connection information back into detailing software, BIM software, so you can then have it in your package and be able to, you know, mark it up as need be, instead of kind of trying to work around some different sketches and things like that. The one other question that I see, is there a way to make a cut based on the edge of a plate?
A cut by what, sorry?
Based on the edge of a plate.
Oh, it might be, instead of cutting it to like the face, for example, it's saying I want to stop it at the beginning or the end of the shear plate, for example. No, I don't think so. It has to be, well, not necessarily perpendicular, but it cannot be creating a cut parallel to something else, even though it would be intersecting. I'm not aware of a way to create this.
And a lot of the cut, I know it kind of adding on, say if you need to leave a 1/2 inch gap. So obviously you have, like, in this cut of member, there is an offset. So you can kind of say what that dimension is as far as for the offset itself. But I know that's not necessarily, and then you just have to turn off the weld so you can kind of leave that gap. I'm not sure if that 100% answers your question. Okay, but for a gusset plate. Okay, I think, yeah, unfortunately I don't, so basically looking at like let's say a bolted gusset plate connection, like a wide flange brace, and being able to make that cut, basically cut the brace per the edge of the plate. Yeah, I don't believe we can do that right now.
Maybe the offset.
Yeah.
In
I just tried, and I just tried on my end, and it was saying that I cannot execute the operation. The cutting plane is parallel to my beam, so that's not working for plates.
Right. So that's something I would definitely pass on to our development team, as that I can understand where that comes up, particularly with brace connections. All right. Haven't seen any other questions yet, or but again, feel free if you have questions after the webinar, you can always feel free to reach out to us directly, myself, Andrea, Jan, or you can just basically the general inbox for the US office is office@ideastatica.com. You can always send questions into that, or contact us directly. Obviously, you can always submit a case through the user portal on our website. So we have a lot of different ways that you can reach out to us. So with that, we're going to end the webinar. One thing I just wanted to mention is we will have another webinar coming up September 21st, I believe.
Yeah, correct.
And I apologize, I forget what the topic is. I believe that's going to be
the BIM links.
Yes, BIM links. So kind of working with using IDEA with other software. So as far as analysis and detailing packages, and kind of showing you how to integrate that information. So that'll be in September. October, we're going to have a guest speaker. Basically, we've been working with several universities over the last few years on some verification work to verify IDEA's results compared to AISC. So we're going to have University of Tennessee on at the end of October to kind of talk about some of the verification work that they have been working on. And if you've been on our website and looked at the verifications, you can see several articles from University of Tennessee Ohio State University, as well as University of Illinois, Chicago. And the plan is that we are going to be mixing those university webinars in with other topics. So yeah, definitely keep an eye on the website, LinkedIn, email. We will let you know as things are coming up. And just to let you know, we are going to be attending several live events in the next few weeks. You can see on that screen. So we have the SEA of Ohio in Columbus coming up, SEA of North Carolina in Charlotte. We'll be at Autodesk University at the end of September, as well as Structural Engineers Association annual conference in Fort Worth, SDS2 Summit, and NCSEA Summit 2022. So a lot of opportunity to interact with us. Hope to see everybody there, and feel free to bring with any questions. So with that, we're going to go ahead and end the webinar. Thanks for your time, and enjoy the rest of your day.